So your do now problem had you calculate the molality of a solution, and most of you were successful there. Molality is just one way in which concentration can be expressed. Others include molarity and mole fraction. We'll be using molality when we talk about the colligative properties later in the chapter. We're going to go back now to molarity, and that's usually the way solution concentration is expressed. We've been talking about solutions, and we talked about some of the properties of solutions already, how to determine solubility rules, or how to apply them really. They will be provided to you, but you will be needing to analyze a solution to see if it's soluble in water, as well as calculate concentration, whether it be molarity, molality, or mole fraction. What we're going to talk about today is whether a solution is dilute or concentrated, how to make solutions two ways, and you'll be doing a little mini lab next week in which you'll be making solutions two different ways. We'll then get into some other terms that deal with solutions, as well as analyzing graphs that illustrate solubility, and you've got another lab on solubility in this chapter as well. In regard to dilute versus concentrated, let's think about dilute versus concentrated as such. Well, let me ask you this. What is a dilute solution? I don't know what you mean. Please tell me. Yeah.
Well, like if something's diluted, that means like the solvent is like dispersed throughout like the water, for example.
So what do you mean dispersed?
So like it's like dissolved.
So if you looked at these two solutions here, which one's more dilute?
The right one, or your left.
This one?
Yeah.
How come?
Because it's lighter.
It's lighter, which means it has
More water.
more water, so more solvent and less solute. So if you were to look at these two solutions, I don't know how well they're going to show under the screen. Do they show? Pretty good. You can see that the one in the volumetric flask, and I'll show you how to make that, versus the one in the beaker. The one in the volumetric flask is clearly more dilute because the color is lighter. So we're going to be making solutions in the lab two different ways, and we're going to talk about dilute versus concentrated solutions. Now, not to be disgusting or anything, but when you get up in the morning, what's usually one of the first things you do? Go to the bathroom, right? After you turn off the alarm a few times, you get up and you go to the bathroom. And first thing in the morning, compared to later in the day, if you've been drinking a lot of water, how does the color of your urine compare? It's darker in the morning and clearer as the day goes on, as long as you've been drinking water, correct? If you're not sure, check tomorrow morning. So first thing in the morning, your urine's very concentrated, and as you drink throughout the day, it gets more dilute. If, for example, you made lemonade and you tasted it and it was way too strong, what would you do to it? You'd add water or put some ice in it, right? You might put some sugar in it if you wanted to sweeten it up. But you would just dilute it. You would add more water. So, a concentrated solution versus a dilute solution. Let's say, for example, that you have one solution that has a concentration of sodium chloride, which is table salt, of 5.0 molar, and you have a second solution having a concentration of sodium chloride of 0.50 molar. Of these two solutions, which one is more concentrated? This one. And when you consider that in terms of molarity, we know that molarity is moles of solute per volume of solution. So in regard to the concentration here, we have 5 moles of sodium chloride per 1 liter of solution. Well, if we look at the concentration here, keeping it at 1 liter of solution, how many moles of solute do we have? 0.5. So clearly what you're seeing here is that the concentrated solution has more moles of solute per same volume of solution. In the laboratory, we've used hydrochloric acid in the past, and we've used concentrated hydrochloric acid at 6 molar. We've also used hydrochloric acid at 3 molar. We've used hydrochloric acid at 1 molar, and later in the year, we're going to be using hydrochloric acid at 12 molar. Which of those 3 is the most dilute? 1 molar. How come?
Because it has the least amount of hydrochloric acid and more water.
But the same volume throughout, correct? Yes. All right, so your total volume will be 1 liter in those cases, or at least the total volume in each case will be the same, but this solution will have fewer moles of solute than this one, okay? So what we want to talk about now is how to make a solution. And there are a number of ways that you can make a solution. There are a number of ways in which you can make a solution. One way you can make a solution is you can dissolve solid in a liquid, and typically that'll be water in the liquid state. That will result in an aqueous solution. Remember, the state of the solution is based on the state of the solvent. In the example in your notes, it says a chemist needs to make, so what you want to make is a sodium chloride solution with a concentration of 2 molar, and the volume of it that you wish to make is 200 mils. And the question becomes, how do we make this? And this is something you're going to explore in the lab next week. How do we make this?
Like mathematically?
Both.
Add water.
But I mean, like in real life, where you just like stir them together.
But how do you know how much sodium chloride to use? Moles first, and then grams. Good. So we know that molarity is equal to moles of solute over the total volume of solution in liters. So the moles of sodium chloride then is going to be 2 molar times 0.200 liters, and that's going to be 0.400 moles of sodium chloride. For every 1 mole of sodium chloride, I have 58.443 grams of sodium chloride, the formula mass that we've talked about for quite a while at this point. The mole to gram conversion we did back in the second 9 weeks, and you were very successful with it. So 0.4 times 58.443 is 23.4 grams. Well, that tells us how much sodium chloride we are going to use, but it doesn't really signify how to make the solution. So to make the solution, and this is what you'll be doing in the laboratory, you will first mass 23.4 grams of sodium chloride in a weigh boat on a balance. And you know how to do that already. You have some lab experience by this point. The second thing you will do is transfer the sodium chloride to a, I'd say, 250 ml beaker. You'll add approximately 150 mils of water. How come I don't right away just add 200 mils of water?
Because you also have the sodium.
You'll also have the sodium chloride in there, which will take some volume. So you don't want to supersede or go over the 200 mils. So you're going to add about 150. And you'll see it in the beaker. You just don't want to get that close to 200. You'll also add a stir bar, and I'll show you what that looks like. And mix on a stir plate, and I'll show you how to do that. For some reason, kids think this is just the coolest thing they have ever seen. I have some sodium chloride that I made earlier in the day, and I added a little food coloring just so you could see the dilute concentrated aspect. And now, if you put it on the stir plate, that magnetic stir bar will start to spin, and you'll get this whirlpool-like effect. You don't want to stir it too hard, otherwise it's going to splash out, and you're going to make a mess, or you could get it in your eyes, which could be very dangerous. So you can stir up the solution. Say it again?
What's the fastest rotation per minute it can go?
It says it can go to 1600 RPM, but that would be like a 2-liter beaker. So, and you wouldn't want that much solution in there because you'll get a splasheroo.
That still looks pretty cool.
It's pretty cool. All right?
What happens if you put your phone on it?
I haven't tried that yet. If you have insurance on yours, I still wouldn't recommend
Wait,
it.
is that thing like, does it have magnets in it?
Yeah, it's magnetic, which can be very dangerous to flash drives, phones, etc.
And credit cards, right?
That's what they say. All right, so you add it and mix on a stir plate until everything goes into solution. So once dissolved, transfer the solution to either a 200 ml volumetric flask. I'll show you what that looks like. Here's a crude drawing where you've got a long neck and then a round bottom there. Or a 200 to 250 ml graduated cylinder. Bring to a final volume of 200 mils with water. Cover and invert, typically 3 times to mix. And this is a volumetric flask right here. This is a 50 mils, so you can only make 50 mils because you basically would take the water level so that the bottom of the meniscus is at the etched line, and then you would just mix it this way. If you had a graduated cylinder, you have more volumes that you can make, although its precision is not as good as a volumetric flask. So whenever you can use a volumetric flask, you should use it. But if you have to make like 220 mils, they don't make volumetric flasks of that volume. And that's how you make a solution, by dissolving a solid in a liquid. The other way that you can make a solution is by dilution. If you have a solution on the shelf that's more concentrated than what you want, you can take some of it, mix it with water, and you'll make a solution with a lower concentration. So another way that you can make a solution is by dilution. And I'm going to show you how to do that. And you're going to be making solutions both ways in the lab, which will further cement these concepts, which are really important. If you were to do any summer work in any type of laboratory, they would want you to be able to make solutions using both of these methods. When you make a solution by dilution, there are a couple of important things to remember. First of all, we know that molarity, capital M, is moles of solute over the volume of solution in liters, as we talked about previously. If I want to calculate moles, then I can calculate moles of solute by multiplying the molarity and the volume. The moles will be constant regardless of whether you have a concentrated or dilute solution that you've made one from the other. And as a result, the same way we expanded upon PV equals some constant K, if the moles of solute is constant, then we can expand upon that formula as such. You've got M1V1 is equal to M2V2. Now the 1 and the 2 was always very confusing for the kids, so highlighted in green is how I like to do it. I do M stock, V stock, where stock is what you have on the shelf in the laboratory. That's going to be the more concentrated solution, the one with the higher molarity. The newer dilute solution is the one that you are making. That's going to have the lower molarity. You can apply this formula a number of different ways. If you look at the first example, it says calculate the molarity of a solution. So you want to calculate the molarity of a solution made by diluting 10 mils of a 4 molar calcium chloride solution. That's what you're starting with. And you want to make 100 mils. So let's take a look at what they're giving you, what you want to know, what the stock is, what the new is, how to tell them apart. So they want you to calculate the molarity or concentration of a solution. You don't know if that's the stock or dilute just yet. Now it says you're going to make that solution by diluting something. If you're going to be diluting something, then that's your stock solution, which I highlighted in green. So the volume of the stock solution is going to be 10 mils. The molarity of the stock solution is going to be 4 molar. So this is the stock solution, the concentrated solution that's sitting on the shelf in the laboratory. We're looking for the molarity of the new solution, the one we're making, or the dilute solution. And we want to make 100 mils of it. Now there are a couple of things you need to recognize right away. What's going to have a higher concentration, the stock solution or the new solution? Has to be stock. The moles will be equal, but the stock solution has to be more concentrated because you're going to make a new solution that's more dilute. So we already established that a dilute solution will have a smaller concentration than a stock solution. They're both going to have the same number of moles, and you can see that however much stock you use, you have to have more volume of the dilute solution compared to what you used of the stock, because what did you also add to make the dilute solution in addition to a little stock? Water, and that's the key. So your formula is M stock V stock is equal to M nu V nu, and you want to calculate the molarity of the new solution by dividing the volume of the new. The molarity of the stock is 4 molar. The volume of the stock is 10 mils. The volume of the new is 100 mils. 1/10 of 4 is 0.400 molar. So the new solution has that concentration, and it's 10 times as dilute. Now if I use 10 mils of stock and I got to a final volume of 100 mils, how much water did I add? I'll say it again. If I started with 10 mils of stock and I got to a final volume of 100, I must have added, as you said, 90 mils of water. Yes.
Is the capital M the unit for concentration?
Molarity, yes. Questions here? So the dilute solution must have a smaller concentration than the stock. Let's take a look at another example. This one's worded a little bit differently. It says, what volume of water would need to be added? So we're looking for the volume of water that we would need to add. We want to add it to 50 mils of a 3.00 molar solution, and we want to generate a solution that's 1.25 molar. Let's try and pull the variables out. On number 2, we want to know the volume of water that should be added. They tell us we have 50 mils of a 3 molar solution. Which solution is that? The stock or the dilute?
Wait,
That would be the stock. That's what you're starting with. So the volume of the stock is 50 mils. The molarity of the stock is 3 molar. It says we want to generate a 1.25 molar solution. What does that represent? Which variable?
And
Which M?
the new
The new one. Good. Now it asks for the volume of water added, but what do we have to get first?
the volume. Oh wait, the grams. No, I don't know.
The new
The
volume.
new volume.
So we know MSVS is equal to M nu V nu. We're looking for V nu, so we're going to divide by M nu. We have 3 molar and 50 mils. We're going to divide that by 1.25 molar, and that's going to give us 120 mils. That's the volume of the new solution, but it's not what they asked me for. They wanted to know how much water I added. So how do I figure that out?
Subtract the volume of what we just got from the volume, the initial volume.
Okay, so it's going to be 120 mils minus the 50 that we started with, and that will be 70 mils. That's the volume of water we had to add. So that's the way you can make the question a little bit trickier. The other thing you could say is you might not specify the new volume with a direct quantity. You might say that you used 10 mils of stock and added 60 mils of water. If you used 10 mils of stock and added 60 mils of water, what would your volume of new solution be? 70 mils. So those are the ways that you can make it a little trickier. All right? All right, we have a second lesson to do. I just want to tell you where you can find these classwork problems. You'll get some more practice here with classwork 3.3, number 12 through 14. We're also going to talk a little bit about solubility today.
Are we supposed to be able to do the whole front and then up through 13?
You're supposed to be able to do through 14, and I'll give you time to work on that today.
But the whole front too?
Yes, yes. I can either stop here and break, or we have another short lesson of about 20 minutes.
Break.
You want to break and then, all right, so in regard to what we talked about, you want to understand how to make solutions 2 ways. Solid dissolved in liquid, as well as making a solution by dilution. You have to be able to do those simple calculations, and you'll be very successful with it if you practice. From the previous lessons, you also want to know how to calculate concentration. Questions here?
How much of 3.3x are we supposed to do? Just the top?
I'll walk you through that in a sec, because we're going to do one more segment. All right?
Up till now it's just the top, right?
Right. Okay.